Hello, this is the short resume video of this Friday, and I have here two windows, one with the exercises and one with some few notes that I have made. Remember, today it is mostly by hand, so I'll show you a few tips in order to do these calculations. So let's see the first exercise here. You should determine the curl of a vector field. There is a hint here. You can look up this theorem. But if you do it in this way, you see the curl of a vector field is a cross product between the nabla operator, ddx, ddy, ddz, I've written here in short form, and the vector field itself. So how I do it is that first, when I should evaluate it, first I put my hand across the upper, say, row of this cross product, and then I take the determinant of the remaining part. So it'll be ddy of x minus y, and that is minus 1. And then minus ddz of the second of minus y minus z. And this will be plus 1. And if you continue in this way, remember then when you put your hand across the second row, you should shift the sign of, say, the determinant of the submatrix. So you get minus 1, plus 1, and finally these two components of the vector doesn't depend on, or you see the second component doesn't depend on x and the first on y, so you get 0 minus 0. So the curl of this vector field is the 0 vector. And this means that if you, and it's defined everywhere in space, and this means that there is an antiderivative to the vector field, and you can find this by actually computing the integral or the curve integral along a stair line, and if you want to find this, there is this hint to the Mabel demo, and look it up because there's a nice illustration and so forth. So find out, and if you use the formula in this demo, then you have these three integrals that you should evaluate. So it's the first component, taking where x and z is 0, it's along the x-axis. So, and it's from 0 to x, and so forth. Look it up and find out. And you see, for instance, v1 is x plus z, and z is 0, so this is simply u. And so forth. And when you do this integration, you get this result. And you could, of course, always add an arbitrary constant to the result. So let's see, this is correct. This was the first exercise. In the second exercise, you're asked to calculate the divergence and the curl of a vector field. Again, what I do is that I write this divergence as a dot product between the nabla operator and the vector field itself. And then you can see, being the dot product, you have the operation ddx on the first component plus ddy on the second component, and then finally ddz on the third component. And this is the result. And you're supposed to evaluate that when x, y, and z are equal to 1, 1, 1. So when you put this into the divergence here, you get the result 2. Again, when you compute the curl of a vector field, then it's a cross product between the nabla operator and this looks like this. Again, you have what I do is that I put my finger across the first row here, and then I evaluate this subdeterminant, and I get, when I differentiate this with respect to y, I get xz, and this doesn't depend on z, so I get a 0 here, and so forth. And remember to change the sign when you are looking at the second row. So this is the result, and when you evaluate that at the point 1, 1, 1, you get that the curl of the vector field V is equal to 1, minus 1, 2. Let's see if we did that. Yeah, this is the result. Now, in the third exercise, you're looking at 3 different vector fields. The first one is what is called the explosion vector field. The vector field is directed in the same direction as the coordinates to the point and equal in magnitude. So the further away you are from the origin, the larger this vector field is. And if you reverse the sign, as in W, you get what is called the implosion field. And the second one is an sort of a rotational field. So you should now compute the divergence and the curl of these. By way of example, I have looked at V here. So if you take the dot product of V with the nabla operator, then you get 0 plus 0 plus 0. That is, the divergence is 0. Whereas the cross product, again, dy of 1 is 0, dz of x is 0. So you get a 0 here. Similarly, you get a 0 here. But for the last one, you get ddx of x. This is a 1. And then minus ddy of minus y, and that is 1. So this is the result. Let's see. Yeah, this is the result. That's okay, and you can easily compute the other the other divergences and curls. And now, for a vector field to be a gradient vector field, the curl of the vector field must be 0. And you see here for the vector field V, you have that this is the curl is different from 0, so V is not a gradient vector field. Let's see. Yeah, and this is the curl of the gradient field is 0 when it's yeah, and you see that E and V are gradient vector fields, but V is not. Now exercise 4. Let's see that we have a function, we have a vector field which is a gradient vector field because this is the gradient of this function, and you should evaluate the curvilinear integral along the straight line from a specific point to another point. But being a gradient vector field, then this integral, this tangential curve integral, as it is called, is equal to the function evaluated at the final point minus the function evaluated at the first point, or the initial point. So when you put this into your formula for f, this is simply the product x of y and z, so that will be minus pi half, and this is 0, and the cosine of minus pi half is 0, and the cosine of 0 is 1. So the result is minus 1. I think that we have a couple of hints here. No, it's not necessary to compute the integral, and there's a reference that you can look up, and the result here is correct. In the vector field B, you're given a parametric representation of the curve along which you're supposed to find the tangential curve integral, and when you look at it, then if you you have the endpoints 0 and 2 pi of the curve, and if you put in 0 in your parametric representation, you get 1, 0, 0. And when you put in 2 pi, that is the other end, you get this value here, and it's also 1, 0, 0. So the two points are the same, and this means that your curve is a closed curve. And you know that when the curve is closed, then this is equal to the circulation of the vector field along the curve. And since V is a gradient vector field, this is 0. Let's see about the hence. Yeah, so that's a circulation, and you can look it up in the e-notes, the reference, and here you have the result. I don't have notes for the next one because it's along the same line. You have to compute the circulations in the plane, and so what you do here is that you have two different curves. This is the unit circle, and this is a circle of radius 1, but with the center at 1, 1, and then you have this vector field. So what you do is that you parameterize the two curves here, and you are in the hint you're given two parametric representations of the two curves, and when you do that and you put this into your into your formula for the curvilinear integral, then you can do the integration and you get these results. So along the curve C1 it is 0, and along C2 it's minus pi half. And this was when you took the computation in the counterclockwise direction, that is the ordinary orientation of your curve. But if you do it in the opposite way, the only thing you need to do is that you need to change the sign of u. That is, then you will then the curve will be traveled in the opposite direction. And you can see here, if you put u equal to minus u, you get cosine u, and sine of minus u is minus sinus u. And similarly for the second parameterization. And now you can do the computations and you get this result. So the first curvilinear integral, well, this is still 0, and along C2 you change the sign, and you always do that when you change the direction of your of this curvilinear integral. So then you're asked to answer whether V is a gradient vector field. But remember that for a gradient vector field, the circulation along any curve should be zero. And obviously the circulation along the circle C2 is not zero, so it cannot be a gradient vector field. And this is what the result is. I won't go through the last exercise. You need to be able to do this, and this is more or less about hand calculation. Your study today in order to prepare you for the weekly test, which is only the week version. It is pointed out, and it will open at 6 o'clock today, and please do it. And if you're able to get 60% correct in this week version of the weekly test, you will get a full bonus point. Please do it. Okay, this is all for today, and I'll